So let me quickly talk about the process for solving the robot dynamics. And in today's class, I would spend some time in formulating the Lagrangian and finding out the expression for Lagrangian, and then maybe giving you some hints on how to take this Lagrangian and input that inside the code. So here is the standard process. Whenever you get a robot, first and foremost, whether it's a two-dimensional robot or a three-dimensional robot, draw a kinematic diagram. That is the first step. Draw a kinematic diagram. Second step is identify the centroids of each connected body. So for an example, in this case, you have a revolute joint, you have a reciprocating piston, and then you have at the end, you have a mass. We are considering the mass of the end effector to be significantly more compared to the revolute joint and the prismatic joint. So the only center of gravity or centroid that we are looking at is that center of mass. Then what we have to do is we have to solve the forward kinematics. And when I say forward kinematics, we need to solve the forward kinematics for translational velocities, and we have to solve forward kinematics for rotational velocities. So for translational velocities, we have to go through the process of finding homogeneous transformations, 0h1, 1h2, 2h3, and whatever it is. Then we have to find out this super important. In the case of forward kinematics, we found out the position of the end effector. In the case of forward kinematics, we found out the position of end effector. When we are trying to solve the equation of motion or dynamics problem, we have to solve forward kinematics for all the center of masses. So what it means is if I have a reciprocating joint, prismatic joint, or a revolute joint, once I know where the center of mass of that joint is, I need to know the forward kinematics for that center of mass. Then once I have Px, Py, Pz's for all the center of masses, in this particular problem, it was very simple because the only mass in this problem was the mass of the end effector. So I could just write down Px, Py, Pz. But once I have the forward kinematics done for all the mass positions, I need to find out the velocity. And each mass will have 6 velocities: Vx, Vy, Vz, omega x, omega y, and omega z. Everyone understood this? Each mass will have 6 velocities. With these 6 velocities, we have to find out the kinetic energy of translation for each mass, kinetic energy of rotation for each mass. In other words, that this is the big expression that you see, mvx square, mvy square, mvz square, and its rotational counterpart. You will write that for each and every mass. Everyone understood this? That will give you your total kinetic energy. Then what we have to do is we have to find out the potential energy. Potential energy expression is usually there are not springs involved. If there are springs, then you would use 1/2 kx square or k theta square, depending upon it's a linear spring or torsional spring, and I will write it down. But you will have n times g times h, where you will repeat the same expression for each mass. And please understand This H is always BTZ. Px or Py will not enter in this equation. Everyone understood this? So these are the steps that you have to follow to get to, at the end, what am I looking at? At the end, I just want this Lagrangian L is equal to T, which is the kinetic energy, minus D, that is the potential energy. Everyone understood? Any questions here? You want me to write down the steps, or you? Yeah.
So get the final equations. Is that for, as you're saying earlier, for each mass, or is that for the whole system?
Lagrangian will be just one Lagrangian for the entire system. So it will have the total kinetic energy of the robot minus total potential energy of the robot. Total kinetic energy is nothing but kinetic energy of the first mass, translation rotation, kinetic energy of the second mass, translation rotation, third, kinetic energy of the third mass, translation rotation. But when you do potential energy, the only thing that you should be focusing on is the vertical distance, because that is where the gravity is. Gravity is not acting in X, gravity is not acting in Y, gravity will only be acting in Z. Everyone understood this? So let me ask you this. Do you want me to write these steps, or can? Okay. Okay. It will not take some time, but robot dynamics. So first, draw kinematic diagram. Then identify masses and center of mass. Then perform forward kinematics and when I say forward kinematics, I really need the velocities, which is translational and rotational for each mass. Fourth, find kinetic energy of each mass. And please understand, the kinetic energy for each mass will be comprising of kinetic energy of translation plus kinetic energy of rotation. Then next step is find potential energy of each mass. And potential energy for each mass is going to be of the equation m times g times h, where h will always be pz. And understand, all this must be in inertial frame or the zeroth frame. Then next, find total kinetic energy, total potential energy, and then So kinetic energy is given as T, potential energy is given as V. So you'll get Lagrangian, which is T minus V. And at this stage, use MATLAB to solve, find equations of motion. So these are the steps that you have to follow. And in the last class, I worked out a problem. What I want to do is, I want to revisit the same problem, but in this case, I want to actually add masses to each joint. So this is the problem that we are trying to solve. And it is exactly same as your assignment problem. So if you pay attention, then pretty much you will get the solution for your assignment problem. So this is the robot. This is theta. And what I'm going to say is, this robot now has 3 masses. So mass of the first link is m1. Mass of the first link is m1. And this mass is actually distributed. So this mass is distributed. And I'm going to say that the length of this link is L1. Then I have this second mass, M2, and this M2 is distributed on this link 2. And then I have this third mass. This third mass is concentrated at the end effector. Everyone understood this? So unlike the previous robot, wherein the mass M1, mass M2, and mass M3, we did not have M1 and M2, we only had M3. Here, what we have is, we have something called as the slender rod. So this slender rod means mass that is distributed across the length. So M1, L1, M2, L2, and M3. Everyone understood this? If you were to follow the process that we talked about, first step is to draw the kinematic diagram, and I will just draw it for my reference. And by now you should be an expert in drawing kinematic diagrams, performing forward kinematics, performing inverse kinematics, etc., etc. So this is how it looks like. So you have the revolute joint, you have the prismatic joint, and then you have the end effector. And then you can assign the coordinate systems and see if all 4 rules are satisfied or not. But at the end, what you should be able to do is, I don't remember how I drew it, but assuming something like this, you got the coordinate systems. And make sure that this coordinate system follows the convention. This is your 0th frame. This is your first, this is your second, and you can perform the forward kinematics. Everyone okay with this process? Any questions here? Now, what I want to do is, let's focus on the second step. In the second step, we have to identify masses. So as you can see that there is this mass M1. So I have mass M1. Where is this mass M1 concentrated? And this is very important. And for this first problem, I'm going to go very slow because There are some concepts that I want you to be absolutely clear, because these concepts are applicable no matter what multi-body dynamics problem you solve. Even if you solve soft robotics problem, same concepts are applicable. So first and foremost is this mass M1 is distributed. Everyone agrees with me? So for practical purposes, this mass M1 is located at the centroid of the first link. So this is where I'm going to say this mass M1 is located. So this M1 is located at the CG of the first link. Everyone agrees with me? Let's look at the mass M2. This mass M2 is going to be located at CG of link 2. And this M3 is going to be located at the CG, which is, since it's a point mass, CG of the mass is mass itself, because it's a point mass. So I found out mass M1 is located at the CG of link 1, mass M2 is located at the CG of link 2, and mass M3 is located at the CG of the link 3. Everyone understood this? Now what I need to do is, I need to perform the forward kinematics and find out the translational velocities of each mass and the rotational velocities of each mass. Are you with me so far? I have to find out the translational velocities of each mass, and I want to find out the rotational velocities of each mass. So in this particular robot arm, since this is a two-dimensional problem, we can write the expression. But how would you do it when you have a robot arm that is three-dimensional? So here is what you do. First and foremost, you perform your forward kinematic analysis exactly the way you do it, which means you will find out 0h1, you will find out 1h2, you will find out 2h3, etc. Okay, you will do this. Now you will find out that, see, this is the first link. So this first link, the mass is somewhere over here. Mass is somewhere over here. What that means is the last column of 0h1, the last column of 0h1 would actually include the distance L1, because that is the distance between the frame 0 and frame 1. Are you with me? The last column of 0h1 would include something L1 cosine theta, L2 sine theta, and maybe this distance A1. And then you will have 1. Yes.
So it would include L1 because that's the length of center mass.
No. 0, when you do 0h1, it will include L1, because that is the distance between the 0th frame and the first frame. Are you okay with me? However, what we want for the dynamic analysis is the position of mass M1. And that mass M1 is at distance L1 by 2. Do you agree with me?
Yeah.
That mass is at distance L1 by 2. So what will happen is you will use 0h1, but you will write something like this: for mass M1, Px is going to be L1 by 2 cosine theta 1, Py is equal to L1 by 2 sine theta 1, and Pz is going to be A1. So these are the same or similar expression that we derived in last class. In case if you are wondering This is my X, this is my Y, and my Z is coming out. Are you with me? So this is my X, this is my Y, this is my Z. So if you see from top, the three-dimensional kinematic diagram, you get this two-dimensional representation. Are you with me so far? Yeah.
So in robot dynamics, we have to set the coordinate on CG.
Yes, in forward kinematics, the purpose is end effector position and velocity. In robot dynamics, we want to find out the position of each mass and velocity. Everyone understood that? Question? Yeah.
So because this arm is moving around that one little joint in the XY plane, why is it is not?
Yeah, it's moving in the
Then why is PZ, what is A1?
so basically A1 is 0 in this case. But if you think about it,
Oh, in that diagram, it's A1.
yeah. Actually, you want me to draw this? I think I drew the three-dimensional diagram for this robot. But A1, as a matter of fact, for this arm is 0. Any other question? Okay. The next step, what I want to do is, we want to find out Vx, Vy, and Vz. Now, in this lesson, I would write these equations by hand, but there's a shortcut. You can actually ask MATLAB to do everything. But I will teach that not in next class, but class after that. So you can use that for your assignment 5. So if this whole thing can be done in MATLAB, but for this class, let's find out the velocities. L1 by 2 is a constant. Cosine theta becomes minus sine theta. Let's not forget the chain rule. Remember the chain rule? So theta 1 dot. Vy is L1 by 2 cosine theta 1 theta 1 dot. Are you with me so far? Yeah.
In MATLAB, do we have to use a separate command other than diff to make sure it includes the chain rule?
No, I'll teach you all that. So don't worry about it. Right now, just try to follow the process. And once we do the MATLAB, I will go through step by step and work out problems. Because this stuff is very important. And if you don't pay attention, you may not be able to follow this. Everyone okay with this? Vx, Vy, Vz? Yeah.
Using chain rule, should it be d theta 1 by dx and then d theta 1 by dy and d theta 1 by dx?
Okay. Chain rule. Sine theta of t d by dt of sine theta by t is the derivative of sine theta cosine theta t multiplied by derivative of theta t, which is cosine theta theta dot. Any other questions? Ask away. If you have any questions, please ask. Because this stuff, you won't, no matter what course you take in dynamics, multi-body dynamics, soft dynamics, multi-body hybrid dynamics, same approach can solve all those problems. As a matter of fact, if you study quantum dynamics, you'll also use the Hamiltonian and Lagrangian principles. Nobody uses Newton's laws at quantum level, by the way, because they don't follow Newton's laws. Okay, now the next part is we have to find out omega x, omega y, and omega z. Now here comes the most important part. When you try to find omega x, omega y, omega z, when you try to find omega x, omega y, omega z using the Jacobian, what do? We do something like this. we have omega x of the end effector, omega y of the end effector, omega z of the end effector. And I will write this equation down. We say 0r1, 0, 0, theta 1 dot, plus if you have second revolution joint, you would add 0r2. If you have a prismatic joint, that just becomes identity, there is no rotation. So 0, 0, theta 2 dot, etc., etc. Do you agree with me? Now, please understand, I'm not interested in finding out the omega x, omega y, omega z of the end effector, but I want to find out omega x, omega y, and omega z of each link. Are you with me? I want to, yeah.
Where's theta two?
Hmm?
Do we have theta two?
We don't have theta 2. So actually, I just wrote the basic procedure. But if you ask me, this does not have any theta 2 because next one is a prismatic joint. But just to give an idea, this is how you solve. Now, what you do is now you are interested in mass M1, mass M2, and mass M3. So you have to find out omega xs for the link 1, omega xs for link 2, and omega xs for link 3. So what should you do is, this is very important, and I want to emphasize this. So let me write this: omega x, omega y, omega z. First, let me write the equation for the Jacobian for a general. This is for the end effector is equal to 0r1 multiplied by first joint velocity theta 1 dot. And in this case, there is no second joint velocity, but let me still write this down. Assuming if you have an R type of robot, R type of robot, you will write 0r2, 0, 0, theta 2 dot, plus 0r3, 0, 0, theta 3 dot. I will solve an R robot, but I want you to understand. This is the end effector. Now, this equation needs to be modified. This equation needs to be modified if we want to find out the angular velocity of each mass. So think about it. For the sake of discussion, this is the side note. Okay, this has nothing to do with the problem in hand. I'm considering an R robot, R robot, something like this. I'm considering R robot, and I want to find out the angular velocity of the first link, angular velocity of the second link. So angular velocity of the first link, angular velocity of the second link, and the angular velocity of the third link. Okay. So I'm gonna say, please understand, omega x, omega y, omega z, link 1 is equal to 0r1, 0, 0, theta 1 dot. Omega x, omega y, omega z of link 2 is 0r1, 0, 0, theta 1 dot, plus 0r2, 0, 0, theta 2 dot. and link 3 is on the end effector. Link 3 is on the end effector. Translational velocities on the link, very important. Translational velocities on the link, they are different, but the rotational velocity of the link is the same, which means whether I have end effector located here, end effector located here, end effector located here, the rotational velocity is going to be the same for the entire link, which means omega x, omega y, and omega z for link 3 is going to be same as the previous expression. 0r1, 0, 0, theta 1 dot plus 0r2, 0, 0, theta 2 dot plus 0r3, 0, 0, theta 3 dot.
Professor,
Yeah,
can you repeat the last sentence?
yes, I will repeat because that is super important and that is not emphasized. Imagine that you have a link. Something like this. This is attached to a motor. The translational velocity everywhere is different because the translational velocity, if this is omega, this is R1, this is R2, and this is R3. Velocity is going to be omega R1, omega R2, and omega R3. So the translational velocities are going to be different. Do you agree with me? But the rotational velocity, no matter you consider this point, no matter you consider this point or whether you consider this point, the rotational velocities will always be omega. Everyone understood this? And that is true in all dimensions. So translational velocities are different, but rotational velocities are same. Are you with me so far? This is very, very important. So I gave you this example for RRR, but as somebody rightly pointed out, we don't have theta 2. What we have is, instead of, this is super important. In the current problem, we do not have theta 2 dot. Do you agree with me? So this term vanishes, but this term still remains. Are you with me so far? So in the current problem, if you ask me, we don't have an RRR joint, but we have an RP. That's it. And when we try to find out the rotational velocity of link 1, the first equation is valid. When we try to find out the rotational velocity of link 2, this expression is also valid, but this matrix is an identity matrix. Why? Because it's a prismatic joint. Are you with me so far? And this guy is 0. Everyone understood this? Okay. So what I'm going to do is, I'm going to conclude the discussion for the first part. So 0R1, 0, 0, theta 1 dot. And I know you guys are smart. This matrix is, can someone tell me? It will be cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 1. Remember this matrix? Yeah, 0R1. Once you perform this multiplication, what you are going to get for link 1, omega x is going to be 0, omega y is going to be 0, and omega z is going to be theta 1 dot. Are you with me so far? Do you want me to perform this calculation or we are good? By now you should be expert in forward kinematics.
So,
Yeah.
generally, 1 part 2 would be identical. Not zero. So you have 0 here, minus 0.
But thanks for catching that. So omega x is equal to 0, omega y is equal to 0, and omega z is equal to theta 1 dot. Are you with me so far? Yeah.
If you remove the first term, 0 or 1, then the equation would be right. So the link to. Because 0 R2 composes 0 R1 plus 1 R2. Now doubt to the second.
This term,
Velocity is about the second.
this link, this equation.
So 0 R2 is already including rotation, but 0 R1 and R2. So
Very good question.
why do we need to write bubbles?
Very good question. So the reason for that is, and let me repeat that what the question is. So the question here is, if you have an RRR dot, if I understand your question correctly, let me emphasize, let me explain that question, and then I will explain you where the confusion is, and I will try to give an answer. So right now, 0R1 is the rotation matrix comprising of the first joint. 0R2 is, if you think about it, 0R2, how do we find 0R2? We find 0R2 by 0H1, 1H2, we multiply those, and we get this 3 by 3 matrix, which is 0R2. Do you agree with me? Okay. So the question here is, 0R2 includes 0R1. Absolutely. 0R2 includes 0R1. But what is the geometric interpretation of 0R2? The geometric interpretation of 0R2, or for that matter 0R3, is something like this. Omega x, omega y, and omega z are the angular velocities expressed in the zeroth frame. And the velocity what you have here, or for that matter here, the velocities here are expressed in frame 2. Velocities here are expressed in frame 3. You cannot directly go from 2 to 0 ignoring contribution of theta 1. You cannot go from 3 to 0 ignoring the contribution of theta 2 and theta 1. Are you with me so far? That's why this matrix 0R2 would include theta 1 and theta 2. So in other words, what's going to happen is this velocity, which is expressed in its local frame, will get transformed to the global frame. And you cannot jump the transformation frames. The way this transformation will work, again, please understand, the way this transformation will work, actually I'll try to explain it here and then I'll try to write it down. I can write this as 0R1, 1R2. So with this transformation, first multiplication will yield theta 2 dot in the first frame, and the second multiplication will yield theta 2 dot in 0th frame. So you need both the rotation matrices. And I will explain this over here. But that's a very good question. Thanks for asking. So 0R2 is 0R1 multiplied by 1R2. Are you with me? Multiplied by, so once I multiply this guy and this guy, what has happened? This everything here was expressed in frame 2. After this multiplication, it got expressed in frame 1. Then once I multiply by 0 or 1, everything here is in the frame 1 will get expressed in frame 0. And please understand, you cannot add dollars to pesos, dollars to dollars, pesos to pesos. You cannot add velocity in the first frame to the velocity in the 0th frame. Everything has to be in 0th frame. Everyone understood this? That's why you have both these. Any other questions? Ask away. Okay. Now I need to follow the. Everyone okay with so far? Online students? Okay. The next part which I want to talk about is for mass 2. For mass 2, now here comes the interesting part. Mass 2 has some translational velocities component and mass 2 has some rotational velocities component. So how do I find out the translational velocities of mass M2? So for that, I need to find out Px, Py, Pz. Now, again, and this could be a little bit confusing, but let me tell you, the final answer does not change. This could be a little bit confusing, but final answer does not change. So, depending upon where you assume your M2 is, basically your effective lengths are going to be different. What I mean by that is, imagine a case where that second prismatic joint is fully compressed or fully extended. So depending upon that, your location of M2 is going to be different. So for an example, if this is fully compressed, then the position of this mass is going to be different. If this is fully extended, the position of mass is going to be different. Everyone understood this? So it doesn't matter. You just choose an equilibrium position in your kinematic diagram. So what I'm going to assume is, I'm going to assume that this mass M2 is somewhere. I'm just going to assume. So I'm going to say, and I think I should draw this. And this is my assumption, okay? Because finally the answer is not going to change. So you have, this is your L1. And I'm going to assume that in my kinematic diagram, my link number 2 is starting from here, and this distance, so this is where this is L2, and you'll face this problem while you're solving the problem. So this is L2. So if I want to find out the location of this mass, the location of the mass is, please understand, this distance, which is L1 by 2, and this distance, which is L2 by 2. And this is what is in the kinematic diagram. Please understand, I assume this. So somebody may say, when I try to perform the dynamics, this second mass is completely retracted. So basically that distance is just L2 by 2. That's fine. Or someone says, when I'm going to do the kinematic analysis, this L2 is fully extended very close to this end point. So the distance is L1 plus L2 by 2. That is totally fine. Everyone understood this? So, and you will face this problem. So now there are, so imagine if someone says that I'm gonna do the kinematic analysis when it is like this, that is fine too. And then this distance is L2 by 2. Someone says, I'm gonna do the kinematic analysis in this configuration. That's fine too. So this is L1 L2 by 2. Are you with me so far? The only thing that you want to be careful about is depending upon where you start, whether you use configuration 1, configuration 2, or configuration 3, your initial conditions are going to be different. Which means the position of link 2 or position of mass M2 at time t is equal to 0 is going to be different here compared to here, compared to here. Everyone understood this? But that will not change your analysis. Everyone understood this? So anyone is fine, depending upon how you choose it. Or sometimes what happens is, if you look at the problem, they will tell you that the initial displacement of the mass is 0, which means at time t is equal to 0, that link 2 is completely retracted. So at that time, what it means is you are in this configuration. And you will face this problem. This is a very practical problem. You'll face this problem when you are going to actually code your initial conditions in your MATLAB code. So read assignment 4, and you will see that I have given some weird initial conditions that are open to interpretation for a reason. And we'll dissect those initial conditions in next class. So Px is, again, we derived an expression for this. So I'm gonna give you so there is something else here. So if you think about it, the initial, so distance d is defined from the initial position. So let me kind of tell you what it means. And this is very important. So in this particular problem, the problem is, first we have a revolute joint, and then we have a prismatic joint. The revolute joint has the joint variable theta, which is theta 1. The prismatic joint has the joint variable d2. In this particular case, I don't know the distance, but what I can say is I would define, and this is very important, I would define my distance d to be from completely closed position. So this is going to be my distance d. This is going to be my distance d. And this is going to be my distance d. And this is very important. So I'm going to say this is my distance d, this is my distance d, this is my distance d. Are you with me so far? So I'm going to define that distance d is distance when that whole arm is completely retracted. So when the whole arm is completely retracted, the distance d is 0. When it is slightly extended, it is extended by amount d. Now what happens because of the distance d defined like this? And this is very important. There is nothing wrong, to be honest with you, there is nothing wrong in defining my distance d from here. And this is a subtle point, that there is nothing wrong in defining my distance d after the end of L1. There is nothing wrong in defining distance d from some other reference on L1. But your equation in position will include that constant offset, but when you take the derivative, that constant offset will become 0. Are you with me so far? I repeat this once again. So depending upon where you choose your d is finally our sign convention, joint displacement. Whether you consider distance d from the end, or whether you consider distance d from this point, or whether you consider distance d from some other point, that doesn't matter. But for the sake of simplicity, I would assume the distance d is equal to 0 when that joint is completely closed. D is equal to maximum when that prismatic joint is completely open. Are you with me so far? So Px, can someone tell me what would be the expression for Px? Is going to be d2. This is d2. We said theta 1 and d2, right? So d2 cosine theta 1, d2 sine theta 1, and Pz, please understand, Pz is in the vertical plane. That distance is not changing, so it would just be A1. Are you with me so far? Then what I need to do is Vx, and now there are two variables. So this will become d2 sine theta 1 dot with a negative sign plus d2 dot cosine theta 1. Vy is equal to d2 cosine theta 1 dot plus d2 sine theta 1, and Vz is equal to 0. Are you with me so far? Okay, the story doesn't end here. Yeah.
D2 dot, just like that. D2 dot.
Oh, D2, yeah, thank you. Okay, let's not forget omega x, omega y, omega z. And I'm going to emphasize here, this is for mass 2, which means the expression is going to be 0r1, 0, 0, theta 1 dot plus, now some of may ask me, this will be 0r1 multiplied by an identity matrix 1 0 0 0 1 0 0 0 1 multiplied by 0 0 0. That means everyone understood, because this is the revolute joint, this is the prismatic joint. I need here 0r2, this is 0r2, this is 1r2. Are you with me so far? So this gives me, what does it give me? Omega x is equal to 0, omega y is equal to 0, omega z is equal to theta 1 dot. And please note, this is for mass 2. Everyone understood this? Same story we have to repeat for mass 3. Are you with me so far? Okay. Okay. So mass 3. Now mass 3, I have to be very careful. Where is this mass 3 located? Mass 3 is the end effector mass. That mass is located at the end of this actuator. Okay. So to find out Px, Py, and Pz, I have to use a consistent sign convention. I need to use a consistent sign convention. At the end, it's not going to matter because the derivative, that offset will be 0. But from understanding point of view, let's understand, let me assume that my D2, this is very important. My D2 is defined, please understand, my retracted position to the center of mass of link 2. My D is defined from completely retracted position to the center of mass 2. Or my D is defined depending upon where this piston is and where this closure is. So wherever you define, it needs to be consistent. So mass 3, I can write down, so, and let me clarify what I mean by that, because this is the point that I'm sure quite a few students will get confused. And this will happen in every prismatic joint that you analyze. So imagine my end effector mass is here. This is my M3. And my closure or the top dead center is here. Okay, so this is where, and for the sake of discussion, I can assume my D2 to be like this, the distance between these two, or I can choose the distance which is D2 from here, or I can choose D2 wherever. But if you look at the way we have defined, is we have defined D2 something like this. Everyone agrees with me? This is my D2. Everyone okay with me? And then this distance, the total distance is L2 by 2. This distance is L2 by 2, which means my M3, which means my mass M3 is at location D2 plus L2 by 2. Are you with me so far? It doesn't matter what reference you choose, but for this first problem, or for that matter, any prismatic joint you solve, this is going to be confusing. So Px is going to be D2 plus L2 by 2 cosine theta 1 Py is equal to D2 plus L2 by 2 sine theta 1, and Pz is going to be A1. Are you with me so far? Now what happens is when you expand, you get this D2 cosine theta 1 plus L2 by 2 cosine theta 1 you will get d2 sine theta 1 plus L2 by 2 sine theta 1. And then this, so when you find the velocities, Vx, Vy, Vz, I need to take the whole derivative d by 2. Sorry, d, this not, sorry, this is not d by 2, d2. This is d2. So this first term here, minus d2, will repeat as is. So I have minus d2 sine theta 1 dot plus d2 dot cosine theta 1 plus L2 by 2 is a constant, sine theta 1 dot and so theta 1 and theta 1 dot, and there will be a negative sign. And then in Vy, I would have d2 cosine theta 1 dot plus d2 dot sine theta 1 plus L2 by 2 cosine theta 1 dot, and Vz is going to be 0. Are you with me so far? Okay. Now for omega x, omega y, omega z, same logic. This is for link mass 2. And since mass 2 and link 2, they are on the same mass, same body, you will have the exact same expression which is over here. Same as 2. Equation 2. And this equation, I will just repeat it 0, 0, theta 1 dot. Are you with me so far? You have to do this for all the masses. Now, actually, for practical purposes, the problem is solved. Except, I'm going to write down the kinetic. Let me write this down. For kinetic energy for the first mass is equal to kinetic energy of translation plus kinetic energy of rotation. Kinetic energy of translation is 1/2 m1 vx square plus 1/2 m1 vy square plus 1/2 m1 vz square plus kinetic energy of rotation is 1/2 ixx omega x square plus 1/2 iyy omega y square plus 1/2 izz omega z square. Are you with me? Ixx, iyy, izz, they are dependent on the geometry. The way you will find it is, if you have weird geometry, create the CAD model or use SolidWorks to find out Ixx, Iyy, Izz. Those are the mass moment of inertia at the centroid of that joint. Mass moment of inertia at the centroid. So in this case, omega x is going to be 0. Omega y is going to be 0. And Izz is going to be, so Izz is 1/12 m1 L1 square. Are you with me so far? Because that, remember, is a slender rod. So this is L1. mass M1 is IZZ. ZZ is okay. Same thing for kinetic energy of mass 2. Same thing for kinetic energy of mass 3. And finally, the potential energy for mass 1 is plus M1 G PZ. Potential energy for mass 2 is M2 G PZ1 PZ2, and potential energy of mass 3 is equal to M3 G PZ3. And finally, you would find the Lagrangian as total kinetic energy minus total potential energy. T minus T. And what I'm going to do is, in next class, I'm going to take all these equations and plug it in the MATLAB and solve the problem. So pretty much your assignment 4 will be solved. But as an assignment, what I want you to do is, I want you to try to program these equations inside MATLAB and then see what results you get. Okay, we'll stop here.